All right. Good morning. Good morning to track 2, Haystack Day 1. It is my pleasure to introduce René Kriegler to you. He is Director of E-commerce at Open Source Connections, a dear colleague of mine, and he has a proven record of e-commerce search success over the past 15 years. He is co-initiator of Chorus, an open source search tool stack, and also maintainer and founder of the Quirky rewriting plugin. And today he'll share his thoughts about how implicit user feedback can be used to optimize e-commerce search. René, stage is yours.
Yeah, thank you, Daniel, and welcome to my talk on modeling implicit user feedback for optimizing e-commerce search. Yeah, I think Daniel has mentioned most of the things, so that makes this slide pretty quick. I just want to mention one additional thing. So we've had the Mises event on e-commerce search yesterday, and I think the feedback I got was quite positive. So it's a one-day event on e-commerce search, and there will be one in Berlin pretty soon, 15th June. So if you can make it to Berlin, please come, and you can still submit a talk to that. So why do we want to model implicit e-commerce, implicit judgments for e-commerce search in a specific way? Why is this important, so important for us in e-commerce search? And yesterday at the Mises event, I presented a model for understanding e-commerce search, and we saw a number of aspects that go into the consumer behavior, why they would buy, and how that would map to search. And it falls into 3 groups. Basically, what is it? What does the user or the consumer want to buy? What do they get? The utility, that thing. And in terms of search, it's more or less the relevance. They're finding smartphones when the user is searching for smartphone. But then there are also other aspects like the actual offer. Is this an attractive price? What's the delivery time? So that's this buying aspect. And then the being aspect. So maybe a preference for a certain brand because I like Jeeps, or I like Apple, or whatever. And it's these last 2 aspects that are very defining for e-commerce search, and that we cannot elicit from a user. We cannot ask them why they have this preference, but we can observe it in implicit user behavior. And that's why getting implicit judgments is very important for us in e-commerce search. So the problem of judgment modeling, so why do we want to have judgments? So it tells us this is a good product, this is a good document for this query, and then we can use this for all types of optimizations. So we need to know how satisfied is the user with a given search result. In non-e-commerce search, that's more or less relevance. In e-commerce search, it covers also these aspects that I've just mentioned. And so the approach now really is to derive this from observed user behavior. I want to introduce a model that has evolved over a number of years, and I've done great pain to many data scientists, I would say, at clients. So we've tried versions about this, and I have to say of this, and I have to say that this is now something practice proven. And the model that I'm going to present shall cover 3 aspects. So first of all, we need a quantification of a success, and I want to model it as an event probability. So how likely is it that a given product or document answers this query well? And in e-commerce search, we would go to click-through rate or conversion rate. So we have many event types that we could consider. And I come back to different event types briefly in a bit. Then also that aspect of certainty that I find sometimes neglected in click modeling. So how sure can we be about this event probability? So sometimes we have few observations, or we have a huge variance in our observations. So that decreases the certainty. And I want to make sure I have this in my model. And finally, we have contextual biases. So we want to eliminate the influence of positional effects. That's the best known effect. But then also device type, mobile versus desktop, grid size on a page layout. So how can we do that? I want to start with clicks. So if you look at the buying decision process, most searches happen in that stage where the user does not make the buying decision. And these can still be very successful searches. Yeah? So we cannot just focus on conversion rate. So typically just 5 to 15% is the conversion rate that we see in e-commerce search, but that doesn't mean all other searches that don't convert are not successful. In fact, the majority of the sessions happens before that, and they're still successful. So clicks it is for now. And I want to use this kind of notion from this book, click models for web search. So how can we model this as a probability? So we get to the first aspect, the probability. And basically, we are looking at modeling a variable that can take two values, 1 or 0, the click probability. And in a very naive approach, we can say, oh, this is just our click-through rate, clicks divided by views for a given query document pair. So that's my C and QD. So QD, the query, D, the document, and that's the clicks, and view is my views. So if you use this naive approach, we might end up with things like this. So we might have 100 views and 20 clicks, all fine. Click-through rate 0.2. And then we have a few cases that have a bit of a smell. So if you look at the two cases where we have 100 views, in one case we have 0 clicks, in the other case we have 99 clicks. Obviously, we should somehow reflect that the 99 clicks is better, and we do this in this model. But then if you look at 0 clicks for just one view, we get the same like for 0 clicks and 100 views. Yeah, so basically they both get 0 as a click-through rate, which doesn't make a lot of sense. Yeah, so we want to express that the case where we have 100 views and 0 clicks is much worse than the case where we have just one observation. And then the two cases where we have one observation, in one case we have 0 clicks, in one case we have 1 click. So 1 click is very extreme, and basically that's our uncertainty. Yeah? So with the next view, we expect that this will probably change. Yeah? And we should do something about this. And I want to introduce an expected value to help us model this. And we could use an expected value for our click-through rate and just use an average of what we observe or a sample. And there are many ways to do this. So in the first row, it's more like a scalar value. But then in the second row, I use two parameters to model this expectation, alpha and beta. Yeah, so alpha and beta, depending on how I choose them, could give me a certain click-through rate. And then later on, I can update my parameterized expected value with the actual observed clicks and views. And this gives me something like this. So choosing the parameter values of 1 and 9, I get an expected click-through of 0.1. And if I update this, that would lead me to my Y column here, that gives much more meaningful values. Yeah, so if you first look at the two cases where we have 1 click, 1 view, they make much more sense now. Yeah, so 1 click over 1 view now is 0.18. Yeah, so, and then we also get rid of the case where we have 100 observations, 0 clicks versus 0 clicks for 1 observation. So this starts making sense a bit more, yeah, if we update that expected value with the actual observations. So this phenomenon is called shrinkage. We shrink everything to our expected value, and we have a nice intuition about it. Yeah? So the fewer views we have, the greater is our uncertainty, and the more everything shrinks to our expected value, and the more observations we have, the more we can move away from that expected value. I want to visualize this a bit. So basically, these dots represent our observations, and the darker the dot, the more observations I have. And in the middle column, I introduce my expected value, and then after applying this, adding the observations to the expected value, we see everything moves to that expected value. Yeah, so that's basically what we say. And the lighter the color, the more everything moves towards that expected value. And I'm slightly introducing Bayesian terminology. So my expected value becomes my prior, and then after updating with the observations, I get to my posterior. The question now is, how can we find good values for these alpha and beta? And I just want to build the intuition about this. So you might remember from the previous example, we had an alpha and a beta of 1 and 9. And then if you look to the left of it, I choose a much smaller alpha and beta, so 0.01 and 0.09. And then to the right, I'm choosing much higher values. And you can see the greater the alpha and beta are, the more they, the greater the shrinkage. Yeah, so, and smaller they are, the more weight I give to my observed values. Yeah, and I think that's a nice playing field, so to say. Yeah, I could say, oh, I have more uncertainty, I choose a smaller alpha and beta, and uncertainty about my expected value, but the surer I am about my expected value, the greater I make the alpha and beta, and then I need a lot more observations to get away from that expected value. So still the question is, okay, 0.1 and 0.9, but could also be, I don't know, 0.2 and 0.8. Yeah, so how do we find the exact values for alpha and beta? And alpha and beta, the way I've modeled this expected value, actually is the way we express the expected value in the beta distribution. So it's one of the distributions of probabilities. It's used for binomial values. And alpha and beta are just parameters of this distribution. And if you look at the probability density function of these, we can see some interesting properties. So if you look at the x-axis, so that's basically our probabilities from 0 to 1. And depending on how I choose my alpha and beta, those probabilities become more likely or less likely. Yeah, so if you look at the, what is this, purple-violet case where alpha and beta are 2, so then I get a maximum at 0.5. And it looks almost a bit like a normal distribution, but it's not. And then if I look at the red graph with very low alpha and beta, I'm basically saying, if I think of this as click-through, yeah, so either I get a click-through or I don't get a click-through, but I hardly get items that gets clicked in half of the cases. Yeah, so my expectation would be something is clicked a lot or not at all. Yeah, and that's something we see a lot in e-commerce. But I can model this by choosing those factors. Still, I don't know how I get the exact values. I mean, I could look at this and then try to model it. But then the beta distribution has some nice properties. So we can use a probability, so let's say our mean CTR, and the variance of that CTR to get this in an analytical way. Yeah, so we could, if you look at these three equations, so alpha somehow is proportional to our success, and beta is then the probability, or proportional to the probability of failure, and then we have this term alpha and beta, and we can get the alpha and beta again dependent on those two probabilities, or that probability, and then the inverse of the variance. And that's a very nice property. Yeah? So we can say if the variance is large, our alpha and beta will be low. Or in other words, if our uncertainty is large, alpha and beta will be low, and we will allow our observations to update these values. Yeah? So a lot. Yeah? So they can influence it a lot more. Yeah? So again, this intuition of uncertainty reflected in that model, I find this very nice. On this note, I introduced alpha and beta as parameters of the beta distribution. But if you look at this, we can derive alpha and beta from just the mean and the variance. So we could also parameterize this as the beta distribution as a with parameters that represent a probability, our mean CTR, and the variance, and we come back to this in a bit. So I've introduced you to the Bayesian world somehow, and I don't want to go into details here, but I just want to mention that we have a prior somehow expressed in our in the likelihood function, somehow expressed in our expected value, and then we have the posterior after seeing our observations to the left. So we have somehow now managed to express a probability and our certainty, which is already great. But as we know in our click data, we have a lot of biases. Yeah? So position bias is well examined, but there might also be something else. And let's look how we can get how we can model this into integrate this into our model. One model to deal with position bias, a very simple model, is clicks over expected clicks. Yeah, so what we do, so the first formula does this for a query document pair that's observed at the number of ranks. So my index variable R is the rank, and then aggregated over the ranks. It looks a bit easier if you look at just at the single rank, so that's what I do at the bottom. So it's basically the actual click-through divided by the mean click-through at this rank, yeah? And or divided by the expected value. This model has a number of drawbacks, and I'll come back to this. But if you look at this from the kind of visual perspective, again, we see we have those expected values, these little bars on each rank, and then the coag clicks over expected clicks will just be the actual click-through over the expected click-through right here. Instead of using the scalar values, we can model this again like we did before. Yeah, so then it becomes the posterior divided by the prior. Yeah, and I will use this intuition later on. Yeah, so if we map these, basically that's the actual clicks, the actual click-through, and in our case we model in the expected value and then divide it by the expected value or by our prior. So basically, what we could do, or what I just showed, going back to the visualization, is we would have to have rank-specific priors. Yeah, so somehow we need to incorporate this. So this is overall a great intuition that we can borrow from clicks over expected clicks. And so then, if you have rank-specific priors, we can do this shrinkage spiel per position. But the problem is we would not only remove the position bias from our model or from our values, but also the relevance. Yeah? So the search engine from which we collected those observations didn't sort the results in the random order. Yeah? So actually what happened is it already put good results or highly scored results to the top. And we would take this out if we use this approach. Yeah, so if you compare what happens between the ranks, then we would say, oh, this is good for rank 2, and that's good for rank 1, but we don't know how the two ranks would relate. Yeah, so that's a problem, and that's why we cannot use coag straight away. But there's a way to deal with this, and I want to introduce the intuition for it. So if you just look at the expected values, so remove our observations here at these 3 ranks, we have an expected value per rank. And then we can go one level higher. Yeah, we can say, also these have an expected value. Yeah, so we say, oh, the expected value at rank 1 is much greater than we would expect across all ranks. Yeah, so we introduce a kind of a hierarchy here. Yeah, so we say, oh, the expected values have their own expected values, the per rank expected values have their own expected values, and we know that the one at position 1 is much higher than we would normally expect, and the ones later on are much lower. So if you apply shrinkage at this point, it's a bit hard to see, I guess, on this No, it's nice to see, it's just here. We can apply the same shrinkage. Yeah? So we can now shrink the expected values to the expected values of the expected values. Yeah? So you get the idea of this hierarchy, and we can model them again. Yeah? So they can also have a mean and the variance, and to apply the shrinkage, we can do the same. Yeah? So we have new parameters here. So I use mu as the expected values of the per rank expected values, and the sigma square as the variance of them. Yeah, so we can apply this hierarchy and then apply shrinkage at 2 levels. And then if we apply our updates here, we would move our observations towards adjoint expected values of these 2 levels. And then basically I introduce the variables here in this visualization. So basically after moving them towards those updated expected values, we get new parameters. So in this case it's this theta and this tau squared. So they represent the new kind of mean and the kind of new variance. And they would be rank specific because they incorporate the general expectation and then the per rank expectation. Another way of looking at this, and this is the common terminology, is this is partial pooling. So as opposed to a model that is unpooled or a model that is just pooling. So we combine the 2 levels. Yeah? So each rank has its own parameters, a mean and the variance, and then these parameters themselves have a mean and the variance, our mu and sigma squared at the top. So showing you the math for that also reflects a nice intuition. So the theta now becomes what we use is per rank, and we would use it for creating our alpha and betas, like in this equation that I showed you initially, and our tau squared represents the variance. And they're just the weighted average of our global kind of mean and variance, plus the rank specific ones. And so that mu here is our global, that's the expected value of the per rank expected value, and then we have those variances, and then the same for per rank parameters. And they are weighted by the variance again. Yeah? So this variance here is the, let's say, variance at rank 3, the mean at rank 3, and then we weight this mean by this variance, and we use the variance of the global parameters to weigh them. Yeah? So, and I think this is a nice intuition again. So if we have very few observations per rank, we would more rely on the global parameters, whereas if you have a lot of observations per rank, then the variance might decrease or increase. But based on those variances, we can say, okay, it's more certain what we have per rank, or it's more certain what we have globally, and then combine the 2. So if you put this together, we can have our price per rank, based on our tau and our theta, and then the posterior would be the same way. We update them, and with the observations we have for this query document pair, and the judgment then basically would be, again, the posterior divided by the prior. I know it's a bit of math, but I hope you're still with me. But I think the main thing is to get the intuition here. So what happens if we have a query document pair shown across multiple ranks? So sometimes we have a few observations at position 3, some at position 1. What would we do? So we can introduce a weight. So you might remember for this rank we use the variance as before, and then just take the fraction of the observations of the views we have for this position of all observations we have for this query document pair. Yeah, so we and then use this weight when we combine it with the global parameters, and in the end we would just update it again in the posterior with all observations we have for this query document pair. This took me very long to figure out. Yeah, I tried to calculate everything per rank and then combine it in the end. But the problem is, let's say you have a query document pair that you observe, let's say at 30 different positions, or let's say 10, it's easier to calculate, and 3 times at each position. Yeah, so then you would allow it to move away from that expected value only a little. Yeah, so it's only 3 observations per rank, and they would only move away a little. But then if you model this into the prior, then you would allow it to move away with all 30 observations with a lot more oomph. Yeah, and then that makes it much less noisy. So we focused on positions now as context, and we have a lot of models out there for click tracking or modeling implicit judgment from tracking that say, oh, I look at what happens at position 1 and then at position 2, and I stop at a certain position. Yeah, so if I assume that the user will stop at that position and then not go ahead with their scanning. Yeah, so those cascading models, how many positions did the users give? Actually, I don't really believe the user does not look ahead, and we cannot assume that users would scan the results sequentially, especially in e-commerce where we have grid layouts. We see that towards the margins of the page there's a certain user behavior that's different, and users probably go back and forth. Yeah, so it's all visual. Also think mobile. On a mobile phone you might have 2 results aligned. So does the user go from left to right or from right to left? So the thumb mostly is on the right-hand side for right-handed people. So we don't really know. Yeah? And I want to illustrate this with 2 observations I've made. So the first diagram here shows what happens depending on this number of search results I have at a position rank. Yeah, so the blue graph here says, oh, this is when I have the click-through rate if I have just 1 search result. This is what happens if I have 2 search results, but what happens at position 1? And this is what happens at position 1 if I have 3 search results. And you can see the more results I have, the further or the more the click-through goes down at the first position. So we cannot just say the user stops at a good document. The user goes beyond that. And the same happens at later positions. And here we see a bit of an artifact that comes from the grid layout. So they had a grid of 5 per row. So basically we see something happens if you go up again towards, if the user comes to the end of that grid. Yeah, so we cannot just assume that there's a sequential scan. The 2 graphs on the right-hand side show that there also is a position bias from the end. Yeah, so that's the click-through rate looking from one end or the other. So the red line is the position at the click-through rate if you go from the first to the last position. So that's more or less what we expect. So it drops from position 1 on. But then the blue graph basically is the click-through rate looking from the end. So if you have 8 results, the 8th is the first, the 7th is the second. Or if you have 10 results, the 10th is the first, and the 9th is the second. And as we can see in the blue graph, there's also a position bias from the end, and it goes up again a bit at the top. And I see this quite a lot. Yeah, so we cannot just assume a monotonic decrease. So what do? If you go back to our modeling, you can say we make no assumptions about the relation between all these positions. Yeah, so if you think about that equation that I showed, we can just say, I don't care. Yeah, so I have my rank-specific prior, and there I go. And that opens the door to modeling a lot more things into that context. Yeah, so we go from rank to context, and so we can say maybe a context is position 1 on mobile, yeah, or position 1 on a 5 per row layout. Yeah, so, and then say, okay, I get my prior for that specific context. And we see quite a lot of change in user behavior per position. Yeah, so I think that opens the door to just removing any bias. Yeah, so any contextual bias, if you can model that. Yeah. So updating the equations is just moving from an index variable r to j. Yeah, so we say, okay, we aggregate per context, or create our parameters per context. And the nice thing is, the more granular you make those contexts, obviously the fewer observations you will have per context, but then you can just rely on your global parameters. Yeah? So let's say you have 300 search results on mobile, probably you won't have a lot of observations at position 287 or something. But you could say, okay, in that case, I just go with my general parameters, and that's this nice property of such a hierarchical model, that I can always go back to a higher level. Combining events. So I've talked about click-through, but there are obviously other event types like orders and so on. And we can model them separately. Yeah? So we can say we have our click-through, and then the variable or the probability that we model is for click-through. And then we might have orders, and we can say, okay, it's just a binary variable again, and everything that's binary can be modeled the same way. And then I combine the two. Yeah? And then I can say, okay, I weigh them, using two different weights. And the same way, and I can use my same calculation, and basically it works the same way. I still have to find those weights, yeah, and I can go and try this out in practice. So one experiment that I do a lot with clients is, once we've modeled those judgments, do not create a ranking model straight away, but try out your judgments in production. So the way you can do this is take a number of frequent queries and just sort the search results by judgment. Yeah, so if you want to optimize a model towards your judgments, that would be your optimal case. Yeah, so that's what you're optimizing for. And that gives you a bit of a feedback loop. Yeah, so you would do maybe 2 or 3 iterations of this, and you might discover interesting effects, but it gives you somehow an idea about how what's going on with your judgments. And you can add more events to this, in this case, it's orders. You can add to baskets, and so on. Everything that's binary in the end, because we're using the beta distribution here, and it's easier to combine this if that's binary. Okay, that's already the end of my talk. So I hope it makes sense to you. Please come to me if you have any questions, and if you want to have more e-commerce fun, search fun, we're hiring at OSC. Thank you.
Thank you. Do we have questions in the audience? Yes, we have one.
Thank you. Let's say if on desktop, if the user search and we show 9 results, mm-hmm. and the user clicks in a grid layout, and the user clicks on the top leftmost, do you count the view for the last item to be 1?
Yes. I mean, it's a tracking problem. Yeah. So it depends on the quality of your tracking. Yeah. So what does it mean you showed it? Was it seen by the user or not? Yeah. So some sites get it right, so that it can say, I know the user scrolled that much down, and I would still count it. That lowers your expected values a lot. Yeah. I've played a bit with implying has the user seen this or not, depending on the last click, but the results got much more noisy. Yeah. So in my experience, it was better just to count it.
So do you think that's a strong assumption, or?
It's an assumption. Everything we do is a model. Yeah. So so it worked for me, and I think adding a model for the probability that the user has really seen that item, for me it added noise. It added more noise than it did good, but it might be the case that you have a nice model for doing this. Or Houston, master.
Thank you, Renee. Great talk. I was curious 2 things about evaluating this in A/B testing. If you evaluated this against other approaches to judgments, and B, if you fine-tune the parameters with online in an online world?
The first question, evaluating against others, yes, and also within this, there is there's some questions to answer. Yeah? So sometimes teams say we don't really trust the prior thing, so we want to have thresholds like the number of minimum number of observations, and so on. And also, these alpha and beta, they look so low. Yeah, let's just multiply them by a constant factor, 1,000, something like that. This has worked out the best. Yeah? Not touching it. Yeah, so stick with the theory, so to say. It turns out to work the best in most cases. Yeah.
Yeah, I had a similar question. So do you know, like, how did you do explicit judgments from users, and how well did that correlate to the judgments the model calculated?
I haven't compared this side by side yet, but I'm highly suspicious of explicit judgments in e-commerce if it is not just about, okay, the query smartphone, is that a smartphone? Yeah, so that's something a manual judge can answer. But then, I mentioned this in my talk at Mises yesterday, if you go to the German website mediamarkt.de, which is an electronics retailer, you enter smartphone, you get 800 smartphones. And that's something, they're all true smartphones. A manual judge would have to say, that's a smartphone, yeah? Give it a 1 or whatever your scale is. And then those popularities, those implicit preferences, also a bit the offer, not just the product, the offer. A human judge might say, okay, I get it, that might be better, but I can't quantify that. Yeah? So my experience with this is, I remember this, I did this once, so I had implicit judgments, but there were a few documents that did not have any judgment. So I tried to add my own judgments manually to it. And the query was MacBook, there were 2 MacBooks, so basically I would give the 2, or each of them, the best rating, all of them. And then it turned out that if I looked further and then saw how the MacBooks were rated online in the implicit judgments, there were also 2 MacBooks, and one of them was got a higher judgment, like a higher click-through rate that was 800 times higher. Yeah, so, and the reason for that was the one with the low judgments was one that had a very high price. Yeah, so no one would actually buy this and not click on this. Yeah, so basically what that means is we might know, oh, the price is important, and if it's a high price, maybe it gets a lower judgment, but we wouldn't be able to quantify this as manual judges. I think they have different scopes. Yeah? So manual judgments is pure relevance for me in e-commerce, and then implicit judgments also incorporates relevance, but also all the other factors, yeah? Brand preferences, and the actual offer, delivery time could go into it. So that's a different world, I would say. Maybe too long answer.
Hi, very similar. Thank you for the talk, by the way. Very similar to the first question. What do you do when there's not like a full grid of results? So, say you have a 50 grid, but there's a nine results or 15 results. How do you scale for that last one being important, and etc.? So
there are 2 ways doing that. So one way, obviously, is ignore the problem. Yeah, so if this that's something to try out, so to say. You can model it, so you can make that one of your contexts. Yeah, you can say, overall, I'm showing that many results, but I only have that many, and that many, like 15 results or 9 results, whatever it is. I make this a specific context. Yeah? But then you would end up with a lot of small context, because for each number of search results, you would end up with a specific context. But you could, in theory, do it. what I've been doing in practice more or less is at some point you would get very small contexts or very few observations per context, and what you could do is say, okay, maybe it's important for the first ranks, but then I say everything greater than, let's say, 30 becomes the same context. Yeah, if I have 30 or more results, it's the same context. You could also incorporate counts from the end of the search result. Yeah, so whatever you want to do. Yeah, so I think I want to convey this intuition. Yeah, so once you have this notion of a context with the rank-specific prior and this global prior, you can play with it. You can take everything out of the equation or leave it in. This is your decision. And I can even take out delivery times. Yeah? So if you say, well, I'm not so much interested in the evaluation of the user towards the whole offer. I'm leaning more towards relevance and maybe brand and whatever. Okay, then I bucket my delivery time somehow and then model it as into one of these contexts.
Sorry. Thank you.
Thank you for the interesting talk. I wonder, this is not exactly a mathematical issue, but when users are clicking on things, they're clicking on the description, not on the full description of the full product information. So if the description, for example, is in the wrong language or makes crazy promises, instant rebate or whatever, which turns out to be false, how does that fit into your modeling?
Yeah. So I want to mention, okay, first of all, in e-commerce search, I would say they click on the image. So, but it's the same point. So I think what you're saying is the users might click because they're missing information on the search result page. And then you get clicks for the wrong reason. And that's something that I have observed teams figure out in that phase where they try out their judgments. Yeah, so when they start sorting by judgments, they suddenly see, oh, our judgment for now, they just incorporate clicks. And maybe now we get a lot of clicks. Oh, and then on the product detail page, the users figures out, oh, delivery time's awesome. Or I can't apply my payment method that I want to apply here. So how do you, but then the question is, how do I make good for it? And I think actually this slide answers this a little bit. So the orders, the final orders make good for it. Yeah? So if you give, so usually you would give orders a greater weight. Yeah? So I think it's usually 10 or 20 times greater than what you get from clicks. And this is the combination of the two would somehow help with that.
Last question.
Hi, thank you very much for this. I have a quite general question regarding how you consider to get to the query document pairs. Because what I frequently observe in sessions is like that someone is searching for iPhone, and among the viewed results, it's not what is desired. For example, the cheap ones, then actually the search is refined, then to iPhone 12, then to iPhone 12, 128 gigabytes, for example. So, and then an event happens, something like a click, an order, or whatever. Yeah. So, would you rather recommend to only to take the direct query view combinations into account, or rather aggregate this over the entire session?
So I think you can use both a bit, but I would lean towards using the immediate response. Yeah, so in the case that the user enters a query and then refines it, so that's two separate cases. Yeah, so the first one would be a fail, yeah, so it's a view without a click. And then the second would be a new search with a new view and possibly a click.
Thank you.
There's one more from Simon.
Okay, well, the very last question now.
I had hoped for a question from Simon.
Have you tried training a model using these probabilities?
Yeah. So I think that has two aspects. So one is, yes, you can train a model, like a standard learning to rank approach is something you can do. This works successfully. Actually, the probabilities, or not the probabilities, the judgments then are not integer values. You know, some of the models want integer values. So what can you do? You either patch your library so it can use these decimals, or you multiply it by a huge factor and then get integers. So that works. The other. Sorry?
You just do a regression model.
Yeah. The other aspect, yeah, lambda mart or whatever you want. The other aspect of it is maybe you also want to rank by this. Yeah? Your posterior could also be a score, yeah? and you can do this. Yeah? So basically you're saying, okay, what do I put in my expected value? Yeah? So basically your that's one step, then you update this, get your posterior. Your posterior basically is a click probability, and you could rank by this. And then you can add more features to it or not, so you can play with that. Yeah? So it opens the door to many things. You get a Bayesian ranker. This leads a bit to the conversation we had before this talk. So sometimes, especially in cases where maybe you have a case where your documents don't rest very long on your index, yeah, like classified as they might go quickly. So you would have to go to features. Yeah? So instead of using documents, you would use features and somehow express a document and the query possibly also by their features. So this is something that you can do. And then you could always say, okay, the model expresses these features, but still all observations I have for these features still have, some of them have more clicks, others don't. Yeah? So that part finally could be left to your judgments, and everything else is your score, so to say.
All right, so thank you, Renee.